Have you ever really considered the invisible force that underpins our absolute trust in technology?
It's something we take for granted, mostly.
Exactly. I'm not even talking about cybersecurity or privacy, though those are obviously huge.
Yeah.
I mean, the basic expectation that, when you do something on a computer, it gives you the exact same result.
Every single time.
Every single time, without fail. Like, what if your GPS sometimes just randomly sent you to the wrong city?
Or your banking app, yeah. Imagine refreshing it and seeing a different balance each time.
Total chaos, right?
Yeah.
It would just grind our digital lives to a halt.
Mm-hmm.
But thankfully, that's mostly not our reality. And the hidden principle, ensuring this predictable certainty, that's what we're digging into today.
The bedrock, really.
Welcome to the Deep Dive. We're looking at excerpts from Deterministic Computations Explained to really get our heads around this fundamental concept, deterministic computations.
Sounds good.
So our mission today isn't just, defining it. We want to cut through the jargon, uncover how this is built into our tech, why it's so critical for reliability.
And the challenges involved.
Yes, and the challenges engineers face making it happen. Get ready to see the unseen architecture of certainty.
Let's do it.
Okay, so let's unpack this. To start us off, can you define deterministic computations? What are we actually talking about here?
Sure. Well, what's fascinating is the core idea seems simple, but it implies this profound level of control.
Okay.
So at its heart, a deterministic computation is basically a predictable process. Give it the same input, and it will invariably produce the exact same output.
Every single time.
Every single time. The key things are that predictability, the consistent input-output link, and crucially, a complete absence of randomness affecting the result.
Right. So no chance involved.
None. It's like a precisely engineered chain of cause and effect.
So it's not just usually the same output or most of the time. It's an absolute guarantee.
That's the ideal, yes.
And the source gives a great, really intuitive example. Think of a simple calculator.
Right.
You hit 2 plus 2, the answer is 4. Always.
It doesn't suddenly decide to give you 5 foot because it's Tuesday or something.
Exactly. It follows a fixed, repeatable set of rules that guarantees the result. It's totally dependable.
Precisely. And for those maybe with a bit more background, you could think of it like a deterministic finite automaton.
Ah, okay.
A theoretical model. Given an input, its state changes are always the same, leading to a predictable final state. It's that kind of rigid, rule-bound execution.
Where everything's kind of preordained by the input and where the system is at that moment.
Exactly.
Okay, that helps. Now, sometimes understanding what something isn't makes it clearer. So that's determinism.
Mm-hmm.
Well, that's the flip side. What happens when you introduce, randomness? What's the opposite?
Yeah, good question. The opposite concept is a non-deterministic process.
Okay.
These are computations where even if you give them the same input, the outcomes can vary.
So variability creeps in.
Exactly. And that variability is usually driven by randomness or maybe factors outside the direct control of the main computation.
So that element of chance.
Yes, the unpredictable bit that deterministic processes specifically aim to eliminate.
And our source material has the perfect everyday example for this too. Think about shuffling a playlist on your music app.
Classic example.
You press the shuffle button.
Yeah.
It's the same input every time, right?
Yep. The action is identical.
But the song order you get, totally different with every single press.
Right. Same input, variable output because of that built-in randomness. That's non-determinism in action.
Makes sense.
And it's not just shuffling music. In more complex systems, non-determinism can pop up from all sorts of places.
Like what?
Well, network latency, for example, messages arriving in slightly different orders, or timing issues in concurrent operations when multiple things are happening at once and trying to use the same resources.
Okay, like a race condition.
Exactly, or even relying on, say, user input timing, or when exactly an external API call returns. These things make achieving true determinism actually quite a challenge in practice.
Right, so we've got this clear difference. Predictable versus, potentially chaotic.
Mm-hmm.
But let's zoom out. Why does this distinction matter so much in the real world? Why isn't it just, an academic thing? Where is determinism absolutely critical?
Oh, this is where it gets really important. Determinism isn't just theoretical. It's the critical foundation for so much technology we rely on.
Right.
It basically underpins what we just perceive as technological reliability. Without it, trust collapses, things become chaotic, like you said, with the GPS or the bank balance earlier.
Yeah, those examples really hit home.
Think about financial software. You absolutely positively need it to be deterministic.
No question.
If your bank balance calculation varied each time you checked, even with no new transactions, well, it would be an unmitigated disaster.
Total panic.
Exactly. It has to be deterministic, so your balance is calculated correctly and crucially consistently. Everywhere. All the time.
That consistency is non-negotiable.
Absolutely non-negotiable for financial systems to have any integrity.
And it's not just the numbers we see.
Right.
The source also points out how vital it is behind the scenes for programmers.
For testing and debugging.
Oh, hugely important, yes.
I mean, trying to fix a bug that only shows up sometimes, randomly, sounds like a nightmare.
It is a nightmare, a real nightmare for developers. If software is acting weird, but it's deterministic, the programmer can use the same input, see the same error happen again, and then systematically track down the problem. They can literally replay the exact sequence of events.
Ah, okay. Like stepping through it.
Precisely. It's
Yeah.
far, far easier to find and fix an error in something that behaves the same way every time. That predictability lets them isolate the issue.
Whereas if it was non-deterministic, you'd be trying to hit a moving target in the dark. Good luck reliably reproducing the bug, let alone fixing it. This is why things like reproducible builds and replayable execution are so vital in serious software development.
That makes total sense. Okay, so we've got finance, debugging, thinking bigger picture. Where else is this demand for determinism absolutely essential? Maybe in less obvious places.
Oh, definitely. Think about scientific simulations.
Like climate modeling.
Exactly. Climate models or maybe drug discovery simulations, testing how molecules interact. Reproducibility there is paramount.
Right. You need to be able to verify results.
Absolutely. If a scientist runs a simulation today and gets one result, but runs it tomorrow with the exact same input and gets a different one, well, the whole scientific basis just crumbles. Determinism ensures their findings are actually verifiable and trustworthy.
Okay, that's a big one. What else?
Well, then you get into the really complex world of distributed systems.
Okay, like networks of computers working together.
Yeah, imagine thousands of servers processing data, or maybe a global database that needs to be consistent across continents. These systems are inherently, you could say, prone to non-determinism. You've got network delays, different server loads, machines acting at slightly different times.
It's inherently a bit chaotic.
You could say that, yet we need them to behave deterministically overall to maintain a coherent single state.
Yeah.
Everyone needs to agree on what the data is.
Wow, okay. That sounds like a massive challenge. How do engineers even try to enforce determinism in environments like that, environments that are naturally a bit unpredictable?
Yeah, it's a huge area of computer science. They use sophisticated techniques. For example, in many distributed databases or systems, you'll find things called consensus algorithms.
Consensus algorithms.
Yeah.
Like Paxos or Raft. I think I've heard of those.
Exactly like Paxos or Raft. These are complex protocols designed specifically to ensure that even if individual machines fail or messages get delayed or out of order, the system as a whole can still agree on a single, consistent order of operations and reach a deterministic state.
So they sort of manage the underlying randomness.
Precisely. They build a layer of deterministic agreement on top of the inherently non-deterministic network communication.
That's fascinating, building certainty on top of uncertainty. And, you know, if we're talking distributed systems, agreement, trust, I can't help but think about blockchain.
Ah, yes. Good connection.
Does determinism play a role there? It feels like it must.
In an enormous role. Absolutely fundamental. Blockchain is actually a perfect illustration of determinism in action in a highly distributed and seemingly chaotic environment.
How so?
Well, every transaction, every single smart contract execution on a blockchain must be deterministic. Think about it. If different computers on the network process the same transaction, but came up with different results, say one node thinks you have 10 coins left, another thinks you have 5, the whole ledger would instantly split and become useless.
Right. The shared record would break down immediately.
Exactly. The power, the beauty of blockchain relies on the fact that every node, starting from the same initial state, and processing the same sequence of valid transactions will arrive at the exact same final state of the ledger.
Guaranteed.
Guaranteed. This shared deterministic understanding of reality is what builds trust without needing a central bank or authority. It's a prime example of engineering determinism for huge implications in security, transparency, and consensus.
It's what makes that history immutable and trustworthy.
Precisely.
Wow, okay. That really puts it into perspective. It's not just about simple calculators or avoiding bugs. It's foundational to these massive, complex, trust-based systems, too.
It really is. Far more than just reliable, it's the backbone making these systems work and be trustworthy in the first place.
Okay, and there you have it.
Uh,
Our deep dive into deterministic computations. We've seen how this principle, guaranteed predictable output for a given input, no randomness, is this essential, often hidden backbone of our digital lives. We contrasted it with non-deterministic processes, where randomness means variable outcome.
Like a shuffling music.
Right. And we explored why this difference matters so much, from making sure your bank balance is always right,
Crucial.
to letting programmers actually find and fix bugs efficiently, to underpinning scientific simulations, and even forming the basis of trust in things like blockchain. Determinism is critical.
For reliability, security, functionality, pretty much everything.
It really is the invisible hand stopping our digital world from just descending into chaos.
Well put.
So thank you for joining us on this deep dive into the hidden certainties shaping our digital experience.
And maybe this leaves you with an important question to ponder. Beyond what we talked about today, finance, debugging, science, blockchain, what other everyday systems or technologies do you interact with that absolutely must be deterministic?
Oh, interesting.
You know, for them to function correctly and for you to trust them. Think about things like autonomous vehicles, maybe, medical devices, critical infrastructure control.
Wow, yeah, the implication.
What would be the truly chaotic, maybe even catastrophic consequences if those weren't deterministic? It really highlights how much effort goes into engineering predictability into our world. Something to think about until next time.